I think most of you are here. So it's time for the second lecture. As I told you, we have mathematicians, physicists, computer scientists, biologists in this institute. And now it's a great pleasure to introduce my colleague from physics, Professor Nemani. He works in string theory, and it's pretty mathematical, as you'll see. He's also going to talk about symmetry. Well, I don't think he's going to talk. Are you going to talk about string theory?
No.
No string theory today, but something called duality, and of course symmetry. So symmetry and duality.
Yeah. Should I start? Okay, so I would like to thank the organizers, but I'm not sure yet. So maybe at the end of it, I'll decide whether I should like to thank them or not. So it's very exciting to see so many people. It's must be a successful program, which I was told has been running regularly. Okay, so today I'm going to talk about this topic, symmetry and duality. Yeah, let's see what it is about. So my aim would be to introduce, yeah. Not very audible. I'm talking at my usual. So should I be talking louder, or because I can't keep up? So is it okay? Is it okay now? You know, as I get excited, you know, I'll get louder. So just hold on. Don't ask for increasing the volume too early, because you may regret it later. So okay. So what are symmetries and why are they important in physics is what I want to tell you about. And I will stick to very elementary examples in physics. And I'm hoping that I'll be able to keep you with me at least as far as possible in this talk. Okay. So what I want to start off by saying is that this concept of symmetries is probably one of the most useful concepts in physics, and I myself use it day in, day out, and it's not an overstatement by any stretch of imagination. The nature chose to describe itself, or the language that we understand nature, is in terms of the so-called quantum field theories, and we have two very, very successful models to describe nature. One of them is called Standard Model, another is called, I don't know why I put a T in the middle, General Relativity, I think General Theory of Relativity. So this is a classical theory so far, and this is a fully quantum mechanical theory. We know what they are, but most of the time we don't understand what they want to tell us. Okay? And most of the time we are guided by what symmetries we expect of those theories, and what symmetries are trying to help the theory tell us something which is tangible and experimentally measurable. Okay. So symmetries, this is an introductory slide, so don't worry if you don't understand. There are two introductory slides. There are some slogans here. So continuous, so they come in continuous or discrete. Two varieties in physics, or anywhere I suppose. Continuous simply means that the symmetry transformations, again I'll tell you what they are in specific examples, have tunable parameters. So you can take the parameters to some specific values when you have done no transformation on the system. Okay. Whereas the discrete ones, the discrete ones have no tunable parameters. You may have heard some such symmetries in the first talk by Amrutanshu Prasad. So examples, a few words, buzzwords, is that in the class of continuous symmetries, we usually use Poincare as the symmetry algebra or the group, and also conformal. One of my aims would be to explain what these two are in some simple context, and gauge symmetries and general coordinate transformations. I will definitely not talk about general coordinate transformations today, but it falls into the list of the useful ones in physics. The continuous symmetries again come in two varieties. One set is called local symmetries, and the other set is called global symmetries. Again, we will know what they exactly mean. Roughly speaking, what global symmetries would mean is that the parameters, the tunable parameters that I just mentioned, are not arbitrary, and they don't depend on space-time points. They don't change from here to here and so on. Whereas for local symmetries, that's the case. So you can make a transformation, symmetry transformation at every point in time or at every point in space. Again, hopefully this will become clearer. So why symmetries? The simple slogan is that more the symmetry you have, more control you have on the calculable physical quantities out of a theory. Again, something that I'm not going to tell you what the calculable physical quantities of a given theory are. I'm going to stick to some simple examples. As I said, this is supposed to be introductory or slogan raising. Okay. So typically, physical systems admit more than one description. So this is another part of the title. So for example, you could be looking at the same audience from a different perspective, or through infrared camera or something which captures all the information, but in a different language. Okay, so that happens all the time in physics. So a given physical system may admit more than one description, and since it's supposed to be describing the same physical system, they have to be equivalent descriptions. Okay. However, this equivalence may not be so obvious. In most of the cases that are useful, these equivalences require a whole development of dictionary which can take decades to develop. Okay? And when it's very difficult, once you know one entry of the dictionary, how to translate one to the other, it becomes more useful than the symmetries which you can establish without much effort. Okay. Okay, so usually they are non-trivial or counterintuitive, and most of the cases when these are more difficult to prove are also when they are more useful. So dualities, describing the same physical system in different languages, is again one of the modern tools in theoretical physics. Okay, so the toolbox required is quantum field theory. I'm not assuming, I will not use it. Okay. And a little bit of groups and representations. Okay. So plan of the talk. So I mean, that's just introduction and probably motivate you to look up further things which are not talked about here. Whereas what I would like to tell you are these three concepts in reasonable detail. These three objects: Galilean group, Poincare group, and conformal group. Okay, they appear in different contexts. So the Galilean group is the group of symmetries which appears in the physical systems of particles, or like mechanical bodies which are not moving very fast. Okay, their velocity in a given frame of reference, for example, a ball which rolled along the floor, its velocity when it's not comparable to the velocity of light. Okay, so that's called Newtonian mechanics, but of course we know that that's an approximate symmetry, approximation to much better description of nature, which is in terms of special relativity. And most of the systems which respect the special relativistic symmetry carry this group called Poincare group, which we'll come to in detail. This is part of the plan of the talk. And if time permitting, I will go to one field theoretic model, which is electricity and magnetism, and that's described in terms of fields, electric and magnetic fields, and their theory was written down long time ago by Maxwell, and that theory is known to have huge amount of symmetry. So I will try to exhibit that symmetry, which turns out to be a conformal symmetry. Okay. So, but since I'm a string theorist and I work on some things which are related to dualities, and in particular dualities which are completely non-obvious, if time permits, I'll try to mention one such duality and how that may be plausible, depending based on the symmetries that we would probably have learned, hopefully have learned by that time. Okay. So let me start. Any questions at this stage? Okay. So the part one, Newtonian mechanics. So classical mechanics is, as I said, the theory to describe dynamics of slowly moving particles, okay, objects which are acted on by some forces. Okay. A typical force would be, for example, if you have a charged particle and if you have a another charged particle, there is a force between them, right? Or if you have a bar magnet and if you put it in, hang it to a string, and it experiences a force because of Earth's magnetic dipole moment. And most of the times we work with symmetries which can be written as gradient of a scale, a gradient of a function v of x. So where x is the position vector of the position of the particle, and most of the time in this talk I will be using Cartesian coordinates for the Euclidean space R3. Okay, Cartesian coordinates x1, x2, x3, or x, y, z, whichever you like. You simply measure them. Okay, fine. So Cartesian coordinates. And so the mechanics is most naturally described in terms of something called a Lagrangian or a Hamiltonian. These two are distinct formulations again of the same theory. So this could be thought of as an example of a duality. Both of them are useful, both of them are, one or the other is sufficient. Okay. But I choose today to describe things using Lagrangian because for no particular reason. Okay, fine. So what is a Lagrangian? Lagrangian is a function of these vectors which are functions of time. So what is this vector? As I said, it's how the position of the particle measured in a given coordinate system as a function of time. If it's moving like this, then there are three functions x1, x2, x3 of time which make up the vector x of t. And this dot means their derivatives with respect to time. Okay, so that's again another standard abuse of notation in physics. And this time, it could also depend explicitly on time. So there is implicit dependence through these two vectors, functions, and possibly an explicit dependence. Okay, so I'm hoping that most of you have seen some physics somewhere in your school days, and where you would have seen Newton's equations. Newton's equations tell you that the force, the acceleration of the body experienced is directly proportional to the force, and the proportionality constant is its mass. Okay. However, a bit more abstract, or a better way of describing is it in terms of this action. Okay. What is it? We had the Lagrangian here, which I'll tell you a few examples of. You take that and integrate over a time interval between some initial time t initial and final time t final. Okay. So what is this supposed to be? So each of these is a curve. Okay, there's the parametrized curve, the parameter is t, and you take this functional, integrate between these two. Okay, what paths? So these are considered, these are called paths as you vary t, path of the particle. Okay, for every path you have an answer for this. So the action is a functional of the paths.
What are the units for the L? What is it? Is it like?
Yeah, units are the energy units. Lagrangian.
Supposed to mean like position, velocity, and time.
Yeah. So, yeah, Lagrangian by itself is not a physical quantity. Okay, Hamiltonian is, which corresponds to the energy, and Lagrangian and Hamiltonian have the same units. But why does one prefer Lagrangian is because in the quantum mechanical description, it's the Lagrangian which plays a more important role than the Hamiltonian. For example, path integrals. So it's the Lagrangian and the action which is more important. But it's completely equivalent to the Hamiltonian, but the equations would look different. As I said, I have chosen this because just out of them. Yeah, Lagrangian and Hamiltonian will have their same units of energy.
So if you integrate with respect to time, then you're getting...
That's right. So you get something which has the units of h bar, angular momentum, and you put angular momentum, and you put a 1 over h bar in front of it to make it dimensionless. Okay? Okay, fine. Yeah? Yeah, S is functions of paths. So where was I? Sorry. Here. So this S, so there's one Lagrangian for each path. So as I said, the path of the particle is this vector, the position as a function of time. So you're taking that path from time ti to tf. So there's a path which is a curve, right? So in R3. And for each such path, there's a number S, which is dimension full, but okay, fine. Then to get the Newton's equations, Hamilton said, no, the paths that are followed by physical particles have to extremize this functional, this is a function of paths. So you vary along in the space of paths, and wherever you find the variation to be 0 is a possible physical configuration. So this is Hamilton's principle. With what type of variations am I supposed to consider? So I am considering Ti to Tf. So I will vary the paths as long as I do not vary the positions at the initial time and the final time. So that is given by this condition. Okay. So the variations are held fixed at the initial and final. Okay. So then there is a simple derivation which says that this is equivalent to imposing these conditions. Okay. These are the so-called equations of motion, Euler-Lagrange equations. Okay. I will not give you the derivation of this. I am sure some of you have seen or will see depending on. Yes.
So basically when you say dou of xti.
Oh, dou of x where? Here. Okay.
Under variation.
Yes.
So you basically say that
Partial derivative of L with respect to that set of variables where I treat x's and x dots as independent variables. Is that what you are asking?
no. Does this mean that at a particular time the particle can exist at only one point? Is that what that means? When you say
At a given particular time, these are classical trajectories, particle will exist only at one position. Is that what you are saying?
no.
Yeah, then that would be right. No,
Dou of xti is equal to 0.
dou of xti, where am I saying that?
Under variation.
Oh, this one, yeah, this is much simpler. So all that it's saying is that I am supposed to consider these paths which, so I am supposed to consider these paths. So let me just consider 2 dimensions for simplicity. So this is x1 and x2. Okay, so suppose the particle at time is outside, so at, well, okay, let me consider 1 dimension. So this is time, this is x, and this is Ti, and this is Tf. Okay, so the paths I am supposed to consider, so it could be any path, right? All that I am supposed to do is to vary these paths as long without varying at these points. There is no variation. I don't know if you can see this. I should have drawn a diagram, but okay. So maybe I'll wave my hands once more. So there are paths. So this is initial position, initial time, initial position, final time, final position. The paths are such that these 2 points do not change. So every path has to pass through these points at those particular times. I don't know how else to say this. So is it clearer? Okay. That's required because, that's required because if you want to make this 0 in the variational problem, you will find some boundary terms which will not vanish unless these are true. Just a technical detail if you are interested. Okay. This is called variational problem. So you may have to add some extra terms to, so if, yeah, anyway, so leave it there. Okay. So for a Newtonian particle, the Euler-Lagrange equation is obtained from a Lagrangian which is of this type, where x dot square is the norm square of the velocity. x1 dot square plus x2 dot square plus x3 dot square, again another standard abuse of notation, and v was the potential which gave rise to this force through the gradient formula. Okay. However, 2 Lagrangians will give rise to the same equation of motions, set of equations of motion, if their difference can be written as a total time derivative of a functional, okay, which depends on x of t's and t's, not x dots. Okay. This is another, I leave it as an exercise to show that if you took this as the Lagrangian and imposed Euler-Lagrange equations, they would be identically satisfied, no condition imposed on the x's. Okay. So 2 Lagrangians will, for classical purposes, will look exactly the same if their difference is like this. Okay. The symmetry in physics is defined in such a way that I start with the Lagrangian given to me and make some coordinate transformations, the configuration space coordinates. Here my configuration space coordinates are just these vectors. Make variations in that. It could be rotations, it could be translations, we will come to examples, in such a way that the variation in the Lagrangian is of this type. Okay. So what it means is that in the initial coordinates or in the final coordinates, the equations of motion will look form invariant. Form invariant is the keyword. They won't be invariant. They take the same form with the same possible parameters that are given to you from the Lagrangian. For example, the mass and various parameters in the potential. Yes?
So what is, does F have any sort of, why is it that,
Yeah.
Are we saying that you're changing, yes, what is F?
Yeah, F has no physical role. So why, okay, what I can answer you is why, heuristically, why doesn't it contribute to the equations of motion? Because the variations that you have considered are local inside the interval and held fixed on the boundaries. Okay? So if L was a total derivative, the S will change from the original S only at the boundaries, exactly where I am not varying the Lagrangian.
So the fact that velocity doesn't appear in that?
The fact that velocity doesn't appear is because you don't want to consider a Lagrangian which has higher derivatives in t. That's to do with Newton. I mean, in principle, you could have higher derivatives in t. This Lagrangian could have x double dot and so on. But then the corresponding Euler-Lagrange equation will also have second derivatives of t, of delta L over delta, double derivatives of x and so on. So there's completely nothing wrong. But Newton said that it should be possible for me to solve the equations of motion if you give me initial positions and initial velocities. That means you get second order differential equations as opposed to higher order differential equations. That means you don't work with Lagrangians which depend on double dots. If f had depended on x dot, d by dt of that would have depended on double dots. So there's no way, if you started with two Lagrangians which did not have second order derivatives, their difference could not have had, f could not have had x, first derivative of x. Okay, fine. Okay, so some simple examples of such a thing. The simplest possible is free particle. There is no force. No force doesn't mean no potential. Okay, think about it. No force is a free particle or a harmonic oscillator. This is the most famous example in physics. The toy model or a spherical, no, so let's not talk about those. So toy models, which are, the first non-trivial example that you would consider in physics, which is not a free particle, is the harmonic oscillator. Not because it's just solvable, but because it's ubiquitous. It's everywhere in physics. Anything that you do in high energy physics can be reduced to a bunch of harmonic oscillator, and that's not an overstatement. Okay, so harmonic oscillator, but I'm not going to tell you what it is more than this. And charged particles and electric magnetic fields, another where there is a potential which depends on velocities. Again, I'm not going to tell you about that. So as I said, in physics, the symmetry transformations are the transformations of the coordinate space, the coordinates xi. Now I'm using the index notation. I'll completely abuse my notation till you get every possible way of representing them. So sometimes I represent them by vectors, sometimes I represent them by components, and most of the time I'll work with Cartesian coordinates. Though you can work in any other curvilinear coordinates. Okay, which give rise to the same equations of motion. That means I take the Lagrangian, I vary it under such variations and see whether the variation is a total derivative. Okay, fine. Now for today, I'm only going to talk about free particle because that's most symmetric. Everything else has less symmetry. So free particle, as I said, there is no force. The equation of motion is just this, because the free particle Lagrangian would be half mx dot square, and Euler-Lagrange equation will tell you that this quantity, which is called conjugate momentum, delta L over delta xi dot, is mxi dot itself, and its derivative d by dt of mxi dot is mx double dot equals 0. So that's the equation of motion for free particle. It just says that the solutions are at most linear in t. Okay, so something moving with constant velocities at most. Okay, so these equations have many symmetries. So this is something that I have introduced to confuse you and clarify things. There are symmetries of the equations, there are symmetries of the system. So symmetries of the equations could be much bigger than the symmetry of the system. Okay, but they will, definitely they will contain the symmetries of the system. Okay, so let me just move on. So the equation has many symmetries, and my symmetry transformations are these such transformations. This prime, by the way, is no derivative here, it's just a new coordinate, okay. And the equation of motion has to be form invariant, and this is the comment I just made, and I'm just going to list you the symmetries, okay, because I know the full solution, but it may take you a little bit to figure out all these symmetries. The first one is that the new coordinate is shifted from the old coordinate by a constant a, constant in time, okay. This should have an index I, I'm sorry, ai, so there are 3 such objects, I apologize. And these are called translations. What it means is that I'm taking this particle here, I'm putting it on a bus, and then sending it off, which is moving with constant velocity. Its coordinates will be, I'm just taking the particle and putting it some other place, or I'm moving myself away from the system by a constant vector a, okay. And we'll come back to the boosts later. Rotations simply are these are linear transformations again on the components treated as a column vector of this type, and the usual definition of rotations is that they should leave the norm of the vector invariant, and that condition tells me that this R 3×3 real matrix has to be an orthogonal matrix. This one is supposed to be 3×3 identity matrix. And most of the time we work with infinitesimal variations, and for such a thing, so again I'm writing in components, so you write x prime as x plus something linear in some parameter omega, in set of parameters omega, and you substitute this into this condition, will tell you that omega has to be an antisymmetric matrix. Omega has to be an antisymmetric matrix. It's a simple algebra. You just take this R as 1 plus delta ij plus omega ij as the matrix, substitute here and read out the first order terms in omega. Okay, that's the infinitesimal condition on the infinitesimal parameters coming from the orthogonality of this thing. Okay. Now, how many parameters are there? So it's a 3×3 antisymmetric matrix. 3, right? And those 3 correspond to 3 angles by which you specify a rotation. So in 3 dimensions, you specify a rotation by 3 angles. Maybe you have some of you may be familiar with Euler angles, or you could also parameterize such matrices by something called Cayley-Klein parameterization, which is closely related to Euler parameters. But you just have to specify some 3 parameters which do not take infinite ranges, they take finite ranges, and the space of parameters is also very interesting for this set of allowed things. So there are 3 parameters here and 3 here. As I said, I forgot the index I here. 3 plus 3 6, and there's one more which are called boosts, the thing that I mentioned by mistake. So you take the particle, put it on a bus which is moving on OMR with constant velocity, and then you measure its coordinates here, right? And its coordinates will look like this, where vi are the components of the velocity of the bus. Okay? So this is also a symmetry. How do you verify? So you have to take this, put this back into the Lagrangian, which is half mx dot square, and then ask how is it varying under this transformation. That should be total derivative. If it's 0, well and good. If it's a total derivative, it's fine, right? Now, okay, so there's 3 more here, so total 9 parameters, 9 continuous parameters. Of course, this condition also allows for discrete transformations, yeah, reflections of one of the space coordinates, right, is part of these things. So this is O3, this is called, so the set of 3×3 real matrices which satisfy this condition form a group, okay, and that group is called the rotation group, or O3, which has as part of it the parity transformation I just told you about. Reflect one of the coordinates or odd number of coordinates, xi going to minus xi. Since we are in 3 dimensions, if you reflected all 3 coordinates, that matrix will have a determinant -1 as opposed to a determinant +1 for the rest of them, because this condition tells you that R has to have a determinant either +1 or -1. So 9 parameters of continuous transformations so far, apart from some discrete ones here. These are all symmetries. Okay, as I just said, it's not very difficult to check that they are invariances, they are symmetries of the free particle Lagrangian. Okay, the next one, the only non-trivial one, is the so-called time translation invariance. Okay, because we don't work with an explicit time as a coordinate but as a parameter, it's a little trickier. So for that you have to declare that my coordinates are scalar fields, scalars, under such time translation invariance, meaning the new coordinate at the old time is given by old coordinate at shifted time. Okay, another way of writing is xi prime t prime is xi of t. Okay, this is active versus passive, but again infinitesimal expansion of this, which is just the Taylor series expansion for each component of the vector, will to first order give me this. Again, dot is time derivative. Okay, so again you consider this transformation, infinitesimal transformation, and you substitute into the Lagrangian and check that it is a symmetry. Okay, it's less obvious, but it is a symmetry. Now this is one more parameter, one more real parameter. We had 9 plus 1, so total 10 continuous parameters worth of symmetries, apart from the discrete ones which we are going to ignore for a while. Okay, so composing these symmetry transformations one after the other has to be the resultant has to be some other symmetry transformation. Okay, meaning I just go from xi to xi prime by one transformation, xi prime to xi double prime. Okay, so the successive two such transformations should be the same as going from xi to xi double prime by one symmetry transformation. Okay, so this is a condition coming from the consistency of saying that these are symmetries. Okay, and that translates into the group composition law, which makes these transformations into a group. So as you probably know, a group is a set of elements with a binary operation, takes two elements and gives you one more element in the group. Okay, it has to have something called identity, meaning you compose it with any other group element should get you the same group element. It should have inverse and associativity. Associativity says that it doesn't matter if you take three things, it doesn't matter which order you compose them, as long as you don't change the overall order. Okay, if the group elements are such that the commutator is identity, okay, meaning A and B G1 G2 composed is the same as G2 G1 composed, then it's also called an abelian group. But most of the cases these are non-abelian, so the rotation group itself is not an abelian group. However, translations by themselves commute. It doesn't matter if I do a translation by A1 followed by A2 or a translation A2 followed by A1. Similarly, these commute among themselves, these commute among themselves, but rotations don't, and time translation of course is one element. Okay, so all these 10 parameter worth of symmetry transformations together has to form a group, and these are the symmetries of the free particle. Okay, so this is called the Galilean group. It's 10 parameters. It's not a coincidence that it has 10 parameters. It's related to what we will see next. So we are more or less done. Well, not yet. So what does it mean? So you have symmetries. Okay, go home or do something. So what it means is that every symmetry leads to a conserved quantity as long as the symmetry parameters are constants. All these symmetry parameters, omega, v, a, and tau, are independent of time. Okay, so then they lead to something called conserved quantities. What it means is that it gives you a functional on the configuration space and the velocities whose total time derivative is 0. It does not change in time. So you must have heard that time translations implies energy conservation, and that follows from a powerful mathematical theorem called Noether's theorem. Again, unfortunately I am not going to tell you what it is. Take a note of it and Google it, whatever. Okay, but the result of applying, so it's a constructive proof, the result of applying gives you these conserved quantities, and by list I will go through the resultant conserved quantities for the free particle. The space translations where the parameter is ai gives the momentum mx dot as the conserved quantity, and rotations give rise to these three, again vector worth of conserved quantities, which is x cross p. This is the usual cross product of three vectors. Okay, and the time translations, of course, as I said, gives you the energy. For a free particle, energy is the same as Lagrangian. There is no difference. It's just the kinetic energy, so you should check that. And only non-trivial thing is for boosts, the conserved quantity turns out to be this particular combination, which happens to explicitly depend on time, whereas the conservation means the total time derivative has to be 0. Again, you can check that if you take the total time derivative of this will give you p, and p itself is a constant because of this, and then when you take the derivative, you'll be left with a minus p, they cancel, and the total time derivative is still 0. So even though the conserved quantity for boosts appears to be explicitly time dependent, but it doesn't vary. Okay, fine. So an exercise, so you can verify that all these are conserved using the equation of motion, which is x double dot equals 0. So the conservation is valid only when you are on classical trajectories given by Hamilton's principle. Okay, good. So one part is done. Any questions? No. Thank you. So next, so we will move on to relativistic. Why? Because of the slogan which says that world is relativistic. We have no escape. Newtonian thing is only an approximation. It's just a warm-up exercise. Fine. But again, I can't give you a whole course on relativity, so I'm going to pick and choose my topics so that it will lead me towards the point I want to make, which is about symmetries and conservation laws. Okay, so let's turn to relativistic particle mechanics. So this is based on these two slogans. Again, I'm not going to use them, but let me read them out anyway. Physical equations are form invariant in any inertial frames, any pairs of inertial frames. It should be. Pairs of inertial frames is that suppose I'm sitting here and suppose somebody is moving away with their own lab at a constant velocity away from me or towards me or any other direction, as long as the relative velocity is a constant, okay, then those are called relative inertial frames relative to each other. And suppose I do an experiment in my lab, okay, and I say that this is the law, this is Newton's law followed by whatever, this particle, this system, this water bottle, this this ball, this spring, and so on. Okay, and the person who is moving away at a constant velocity from me or towards me has to, when he does the same similar experiment on the same object seen from his frame, has to come up with a similar looking equation. The equation has to be form invariant. That's what we call covariance of the equations. Okay. So, and then the other assumption is that the velocity of light does not depend on how fast you are moving or your apparatus is moving. So these two are the basic assumptions, basic postulates of the relativistic mechanics made by Einstein, and they were based on sound physical observations. There's something called Michelson-Morley experiment and many thousands of other experiments which have corroborated these two. Okay, so you will find again, yes.
So when you say inertial frame is only at a constant velocity,
yes.
do you have a restriction on the velocity, like
Relative velocity, constant relative velocity. So it doesn't matter. Yeah.
okay.
Yeah. So what it means is that this is something that is called Newton's relativity. Newton's relativity simply means that when you're a kid and sitting in a train and there's another train on a parallel platform and that's moving and you have no other frame and you will be surprised, have we started? Are they moving? Are we moving? So this indecisability or so that thing is called relativity, and that's that is lifted to special relativity by this statement.
Can it be speed of light?
Speed of light in what?
Relative speed.
Relative speed.
Can the velocity be the speed of light?
Can the relative velocity be the speed of light if you have infinite energy to spend? Yes, but for all physical processes, no. Any other question? So it requires infinite energy, as we will see shortly, to kick yourself up to a velocity of light. Any other? No? Okay, good. Again, I'm not going to use this because I've chosen to follow Lagrangian path, but you can just Google derivation of Lorentz transformations or something. They will give thousands of, maybe not thousands, a few different looking derivations based on just these two assumptions. Again, I'm going to take, because it's 100-year-old story, we don't have to reinvent the wheel, but the modern language is that you start with the Lagrangian. So you write down the Lagrangian. How do you write down the Lagrangian is where the symmetries go in. So you know already that there are a set of symmetries which are responsible for these postulates. Once somebody tells you those symmetries and asks you to write down the Lagrangian, once you understand those symmetries, you would come up almost uniquely with this Lagrangian. So that's the power of the symmetries. And the assumption that the physics has to reduce to Newtonian mechanics in the small velocity limit, which is not stated explicitly usually. Okay. So this is the Lagrangian. What does it mean? So there is a parameter called m naught. I'm calling it m naught as opposed to m in the non-relativistic thing. This c is the velocity of light in the vacuum. This is the maximum possible velocity according to the postulates of relativity, which is like 300,000 kilometers per second. Okay, 3 lakh kilometers per second roughly. It's slightly less than this. It doesn't matter. And this x dot square again, x1 dot square plus x2 dot square plus x3 dot square. We are still using Cartesian coordinates for R3, but you are free to use any other coordinates if you liked. Okay. So now to see the symmetries, what's the quantity, what is the integrand of the action? Action is still the same, integral L dt. So you start with that guy and then make these formal manipulations. Push this dt inside and write it as dt square, and then this is dx by dt whole square. Write it as dx square. Okay, and then pull out a c square, cancel one power of c outside, and then that becomes minus m naught c square root c square dt square minus dx I dxi, where dot is the dot product between these two infinitesimal vectors. Okay, the standard notation for this is called the line element of Minkowski space. If you haven't heard this before, you are hearing it now. Line element of the Minkowski space, which means that, you know, if you take 2 points close by in space time as a geometry, which is a concept that you have to get used to because, you know, there is no escape, then writing it like this gives you an interval which is invariant under the symmetry transformations we are going to talk about. This is a generalization of the rotations being, or rotations plus translations being the symmetries of the distance between two position vectors, r1 minus r2 vector mod square, right? If you make simultaneous rotations on them and simultaneous translations of both, that's invariant. So it's a similar statement of that kind, but it's infinitesimal, where this eta mu nu is a symmetric matrix. Again, using the abusive notation of physicists, I write it as a matrix like this. What it means is that the only diagonal entries are non-zero, and they take these values in an order. The first diagonal is -1, second diagonal, third diagonal, 4 or ones. Okay, and then x naught is Ct. So x mu nu run over 0, 1, 2, 3. 0 has been introduced to take care of the time coordinate. So written in this fashion, you can immediately see, since this looks like a, you know, mod square of the distance between two vectors, but in a rather funny space which is called Minkowski space, 4-dimensional, whose coordinates are x0, x1, x2, x3, then you can make a transformation like this: lambda mu nu x nu plus a mu. This has to be real, so this is a real 4x4 matrix, and this is a real 4 vector. Constant in x's. Okay, then you again substitute here and say that this should be invariant. Will immediately tell you that these lambdas cannot be arbitrary. They have to satisfy this, the component notation, they have to satisfy this. As matrices, this simply means that lambda transpose eta lambda in that order should give you back eta. Okay. But in physics we like, we love our indices. The other thing I should mention is that what has happened to these indices, these repeated indices, by convention I will not put a sign. What it means is that there is a sum over mu from 0 to 3, nu from 0 to 3. I have omitted this because there is no ambiguity in omitting them. Whenever I write something, I will write at most 2 indices which are repeated, and when they are repeated, there is a sum which is carried out. These are called dummy variables. The dummy indices, these are like integration variables, but we don't specify the sum explicitly, and you will lose nothing by dropping the sums. But if you don't like that, put the sums, so it doesn't matter. So then the action is clearly invariant because the integrand would be invariant and the action will be invariant. Again, so how many parameters are there? So these are 4 by 4 matrices. Okay, I'll probably come back to the counting of parameters here. So let me just tell you what the conserved quantities are. So using these symmetries and Noether's theorem, which I'm refusing to tell you about because it will take time, you can immediately calculate the conserved currents, right? So for 4 translations you get 4 conserved currents. This is a vector worth of conserved current, this is another conserved current, and the conservation simply means that these are time independent, p mu's are time independent, those are the equations of motion that you should obtain, and this is the famous formula you would have seen as E equals mc square, where m is all this but the c square factor. So the m is velocity dependent if you want to think in terms of that, or there is only one quantity for a particle which is called m naught, which is the rest mass, okay, which has invariant meaning. Every other mass does not have any invariant meaning, okay, in particular that mass. But this is the famous formula E equals mc square, which just pops out of this Lagrangian as a conserved quantity following Noether. These quantities, however, are constrained, they are not independent, and if you can check it for yourself, E square by c square minus p square only depends on m naught and c. Okay, this constraint is actually a consequence of a hidden symmetry of the Lagrangian that we wrote down, okay, which is once you treat x naught as a coordinate and an arbitrary function of some other variable tau, then there are reparameterization invariants for that parameter, but let's not go into there, I think. Yeah, so this constraint is because there is a hidden symmetry which we gauge fixed, which we are not using. Okay, so this means that these quantities also make up a 4 vector and transform as a Lorentz vector under Lorentz transformations. So under Lorentz transformations, energy changes, P changes, but only this quantity has to be held fixed. That means energy and P made out as a 4 vector with upstairs index. So how do I go from upstairs index to downstairs indices? If you haven't seen this before, this is a very sacred positioning, not mine. Upstairs indices and downstairs indices are inequivalent. To go from upstairs to downstairs, you have to use an eta. So for example, x mu up is eta mu nu up, which is just the inverse of eta that we wrote down, times x nu, and vice versa. I don't know, there's no point in writing because you can't see anything here anyway, and then lights take a long time to come on. So this transforms in a way, this also transforms in a different way. Please note the difference. The second index is contracted with this. Here the first index is contracted with this. This is the usual statement that, you know, if a linear transformation acts on the vector space and it acts on the dual vector space through transposition, and that's the transposition that goes here. Okay. So again, successive applications have to close, right, and by symmetry arguments, and again that has to form a group. Okay. So what's the identity element, you might say? Identity element will correspond to lambda being 1 and a being 0. Where is my transformation? Yeah, here. A being 0 and lambda being 1, identity 4 by 4 matrix clearly satisfies lambda transpose eta lambda is eta. Okay. That's the identity Lorentz transformation. And so this is the group composition law. So every symmetry is given by a lambda and an A, and so this corresponds to one group element followed by another transformation, and this is the group composition. You have to check this. So take the transformations I have given, do them successively one after the other, and write the resultant as one single transformation, read out the resultant lambda and resultant A, and that's what you get. Okay, so lambdas have 4 by 4 matrix representations, but as 4 by 4 matrices, P cannot be represented, P, and this is not a faithful representation for P's. What was P? A, the translations, I'm sorry, not P, the A's. Okay. However, if you went one high up in dimension, so if you are allowed to write 5 by 5 matrices, I can represent this group faithfully through matrix multiplication, and that's this. It's a terrible notation. So this simply means that it's a 4 by 4 real matrix, and this is a column, this is a row of zeros, and this is just one There's no matrix. Okay. Then you take two such things, lambda 1 a1 0 1 multiplied on the left by lambda 2 a2 0 1, multiply them and it will take the same form, okay, and then you read out the resultant lambda a, and the lower row will be 0 and 1, and that will give you this. Okay. So this group is called the Poincare group. The number of parameters is 10 again. To count that, so you first start with the Lorentz subgroup, which are made out of lambdas, and this condition gives you 6 parameters. This is similar to the 3 we got. So there was an antisymmetric matrix which generated the parameters, 3 by 3 antisymmetric matrix. There is an analog of that which is 4-dimensional. Eta times that matrix has to be antisymmetric. So a 4-dimensional antisymmetric matrix will give you 6 parameters as opposed to 3 in the R3 case. So this has 6 and then 4 coming from A's. A was a 4 vector, A0, A1, A2, A3. So total 10. And one important, so again as I said, for rotations there are discrete transformations included, right? Time reversal or spatial parity are part of these transformations, but apart from those, the ones which are continuously connected to identity are of interest, and that group is called SO1, 3, or just the Lorentz proper orthochronous or Lorentz transformations. Never mind. So again, as I said, mostly we work with infinitesimal transformations which are connected to identity, right? So here I am going to give you 2 examples of representations of the Lorentz group as abstract things, okay, and then we will leave it there as far as the Lorentz group is concerned. Okay. We have already seen one representation of both Lorentz and Poincare as 5 by 5 matrices. Lorentz itself has a 4 by 4 matrix representation, but that's a solution. Okay, let me not jump the gun. So write lambda as identity plus a small matrix. By small I mean whenever you find higher powers of m, you just drop them. Okay, this is called infinitesimal transformation. Then you substitute this answers into this equation. It will immediately give you an equation for m, which is m transpose eta plus eta m has to be 0. This is the analog of that omega matrix in R3 being antisymmetric. Okay. And as I said, there are 6 parameters in any such m, and then you can take a basis for these 6 parameter matrices m, and the basis that is chosen is of this type. I take 6 unit in some sense basis vectors for these. So these m alpha beta are 4 by 4 matrices. It's just that they carry 2 labels, alpha beta, and when you interchange these two, the whole matrix picks up a sign. That's what this equation means. These are, pardon my notation, these are not the indices of a matrix. These are labels of a 4 by 4 matrix. Now that 4 by 4 matrix has indices mu and nu, and this spells out those matrices. And you should check that these matrices for the set of alpha betas, alpha and beta run over 0, 1, 2, 3, and alpha beta is antisymmetric, so there are 6 independent ones. As matrices they are linearly independent, and any such matrix can be written as a linear combination of these. Okay, and so call these matrices m alpha beta, and then take the commutators m alpha beta, m gamma delta, and then it turns out that they can again be written as a linear combination of m's. So that's a particular matrix solution of a more abstract thing called Lie algebra of SO1, 3. I just flashed it here because you can brag about it that you have seen it, or you may have seen it already. So this is how in my notation this is the form it takes. The commutator, or this is called Lie product of 2 elements of this so-called Lie algebra, is given by a linear combination. This simply means that in the first 2 terms, wherever you see alpha replaced by beta, simultaneously gamma replaced by delta, and write those 2 terms. The right hand side will have 4 terms. Okay, so this is an example of a Lie algebra, which is a generalized. So of course, these alpha beta take 0, 1, 2, 3, right? So 1, 2, 3 indices are represented by I and j usually, and when they are I and j, then there are 3. When 0i, there are 3 more generators, total 6 generators. Okay, these are called generators, else are called generators of the Lie algebra, and these correspond to just rotations in space. Nothing fancy. The same things that we had seen in the Galilean transformations. whereas these are generalizations of the Galilean boosts, xi going to xi minus vit. Exercise. So start with this 4x4 matrix. Okay, come up with some simple examples. 2 by, which is block diagonal. 2 by 2 is non-trivial. Everything else is identity. Okay, and try to solve for the 2 by 2 using this condition, and then you will see that once you parameterize those group elements, that block 2 by 2 block appropriately, it will be equivalent to the textbook way of writing Lorentz transformations as x going to x minus vt by square root 1 minus v square by c square, t goes to t minus vt by x c square, vx by c square square root 1. So I'm just singing. So those are standard things and they come from here. Okay. So this is one particular solution to this abstract thing called Lie algebra of SO1, 3 or Lorentz transformations. But we had much more than Lorentz transformations. We had Poincare, 10 parameters. There is only 6 generators. The remaining 4 are represented as p's, but in terms of 4x4 matrices we represented p's by zeros, whereas with 5x5 you can represent them as matrices, as we had seen, and this is the generator now. And the abstract algebra says that the commutators of else with p's have to be particular form. Okay, and that particular form can be rewritten in terms of this 4x4 matrix, which already provided a representation, and this is not a coincidence. It just says that under Lorentz transformations, rotations and Lorentz transformations, this 4 vector p behaves like a vector. So what it means is that these m's are called the vector representation of the Lorentz group, or Lorentz algebra rather. Okay, if it means something. So that's where we are. So another useful way of thinking about the Poincare symmetry is as it appeared inside the square root of the particle mechanics, which is the line element. So if you take that line element, which we call the metric sometimes, even though many people use different languages for that, and then say that I am going to make a transformation here which takes x mu to x mu plus psi mu. This is again the version of infinitesimal transformation we had made, where lambda was written as 1 plus m. Okay, then psi mu is supposed to be infinitesimal, but doesn't mean that it cannot depend on x. It doesn't mean that it has to be small. It just means that higher powers of psi will be ignored. So then this changes to this guy. It's very easy to check. So the variation to first order in psi is this bracketed quantity. So if this was 0 to, that means infinitesimally, then this line element will be invariant. So this equation, even though it may look complicated, it's a symmetric 4x4 matrix worth of equations, right? 4x4 symmetric matrix worth of equations, but they're very easy to solve. Very easy to solve because when psi is a constant, of course it will be 0. But when psi is some omega mu nu times x nu, where omega is an antisymmetric matrix, also this will solve. And you can convince yourself that the solutions to this are at most linear in excess. Okay, and then that will complete solving these. The general solution to these has to be of the form. Again, as I said, psi's index can be raised or lowered using the eta. Am I blinding somebody by? Okay. And this is the solution. So this is constant and this is linear in x. The only condition on omegas is that it has to be antisymmetric when both the indices are down or up. Doesn't matter. Okay, this is the analog of this condition for the matrix. It's identical really. So, now, once you have these vectors, there is something called vector fields. You can make a differential operator out of them by contracting them with the partial derivatives del mu, where del mu is 1 by c del t and gradient. I should have written it here. So when you take that gives you a vector field. Okay, and it turns out, because of the nature of this equation, take these vector fields and then take commutators of those acting on any arbitrary function of the space time. They close, meaning it can again be written as vector fields acting on the function, a particular combination of those vector fields. Okay, I should have done it, but since I haven't done it here, I am leaving it as an exercise. take two such things, psi1 mu del mu, psi2 nu del nu, take their commutators for that particular size where A1 omega 1, A2 omega 2, right, two different things, and you can convince yourself that they close as an algebra and they satisfy exactly the same algebra as these matrices did, which was this. So what it means is that we have found one more set of quantities apart from the 4×4 matrices here, which satisfies this Lorentz algebra, and this is in terms of differential operators. Okay, this is another representation that we use in physics very often. Okay, so there is a 4×4 vector representation and then through differential operator representations. Okay, very good. So again, the vector field will take this form, and then you can actually not only represent the Lorentz transformations, you can also represent the Poincaré transformations through these derivatives, and then the commutators will satisfy the Lorentz algebra, which is given by this line, and the Poincaré algebra. You might be wondering why I haven't written down the commutator of 2p's, because it simply vanishes. P's commute. This is the fact that the translations themselves form an abelian group. It's a reflection of that. Okay, so there is a reflection of the Lorentz and Poincaré, and they play a very big role in field theories. So part 2 has come to an end. Any questions? Now we are going to move away from mechanics, talk about one example of field theory. Fine. Okay. So symmetries of electrodynamics. I'm again assuming that you would have seen some electrodynamics in your schools. Okay. So what is electrodynamics? It's about how electric fields and magnetic fields interact among themselves or interact with charged particles. So electric field, Maxwell told us, and many other eminent people told us, that can be quantified into one vector field which depends on every position and every time in general. Similarly, magnetic field. Okay, most of the time one works with the so-called potentials. This is the electrostatic potential or electrodynamic potential, magnetic potential. From these two potentials, you obtain these fields through these relations. So B is curl of A is a vector. E is negative of the gradient of phi minus partial derivative of A with respect to time. These are the definitions. Okay, this is well established, obtained from experiments. Nothing, no funny business here. Okay, so the equations of motion satisfied by these were written down again long time ago by Maxwell. So for today, I am only interested in equations satisfied by E and B in regions of space where there are no charges, there are no currents, there are no magnetic sources. Then the equations take, so that's what I mean by empty space, these form. They may look complicated if you are seeing them for the first time. They may not mean much to you, but this is part and parcel of being physicist. This is 200-year-old or something. So these are the equations. These are the famous equations. How many equations are there? This is a scalar equation and this is a vector equation. Similarly, this is a scalar equation and a vector equation. So total 8 equations. Okay. So, but I just told you that E and B can be written in terms of A and phi, like so. So you can actually, when you write them in terms of phi and A, it turns out that these two equations are identically satisfied. Yes?
Maybe you want to mention more familiar names for some of these which they may have seen, like Gauss law and Ampere's law.
Yeah, Gauss law and Ampere's law, but yes. Do they make more sense to you? Gauss law, Ampere's law. So there are integral forms of these equations. There are integral forms of these equations, completely equivalent. Those were the ones which were obtained through experiments, not these ones. When I said these are obtained through experiments, I was not telling you directly the truth. What were obtained were the integral expressions. For example, if you have some charge distribution in this space, but you are given an apparatus which can measure the electric field. Okay, so then you can take something called Gaussian surface, a surface, and then take the electric field normal to that surface, and then take the dot product of the electric field at every point with the normal to the surface, and just integrate that quantity along the surface will give you the total charge inside. So that's called Gauss law. There's something called Ampere's law. It's given in terms of how loops carrying currents behave under magnetic and electric fields. So these are integral expressions, integral equations for exactly the same quantities. So if you are more familiar with those, and if you have not made this transition, it's again something which is done in every textbook. You should do it. And this is much more, I mean, both are extremely useful representations. So differential equations versus integral equations. Okay, fine. Yeah, so what I was saying that once you parameterize, if I may use that word, E and B in terms of the electric and magnetic potentials, as in the previous here, then these two equations are identically satisfied. Why? Because divergence of curl is 0. So B is curl of A. So I'm sorry. So this is identically satisfied. Similarly, curl of gradient is 0. So when you write E as a gradient plus something, this term does not contribute. Only term that contributes is minus del by del T of curl of A. But the second term is del by del T of curl of A. So they cancel. So these two equations are identically satisfied once you parameterize E and B in terms of potentials. So then you only have to worry about these. So it reduces the problem down to just 4 equations as opposed to 8 equations. How am I doing with time? So till 1 is it? Or is it till 1 officially? Okay, so fine. Last 10 minutes for questions? Yeah, that's fine. Okay. Very good. So then we are only responsible for these equations. But I want to point out something. Yeah, the simplest solutions are the light waves to these equations. The simplest solutions are the light waves. Again, I'm not going to do this for you because that will involve giving you a course on electrodynamics. And the light waves, there are experimentally measured parameters that went into these integral equations that were mentioned, which are also here. And those parameters are called mu naught and epsilon naught. And if you take those numbers and multiply, and it turns out that it's exactly bang on target to be 1 over c square. So if somebody thought, you cannot measure the velocity of light without actually taking light beams and so on, no. You measure some electrical susceptibility, magnetic something, take those numbers and take a product. That's another way of getting the number C. And it's miraculous that, using desktop, tabletop, Thomson used to do these desktop experiments. You can get numbers whose product is velocity of light. And the fact that it depends on velocity of light is a hint that these equations are Lorentz invariant and probably Poincare invariant. And in the rest of the time, I will try to convince you that these equations actually have bigger symmetry than Poincare, which is the conformal symmetry. That will be the last part. Okay, so let's move on. Right, so those are the famous solutions, and these are famous examples of Lorentz covariant equations, and this is one of the first things that Einstein himself had done for physicists maybe to show that Maxwell's equations are Lorentz covariant. But let's go through it quickly, but I will not do the way people have done. We don't reinvent the wheel, we'll do it in a bit more modern language. So before I do that, I want to point out one more symmetry. Once you parameterize E and B in terms of this, there's a huge extra symmetry, infinitely, I don't know how to say that, infinitely many parameter worth of symmetry, continuous parameter worth of symmetry. That's because, look at this E, right? So B depends on curl, E depends on gradient. So if I shift A by a gradient, B will not change, curl of gradient. Okay. And then simultaneously, if I shift phi, this particular time derivative with a minus sign, then it so happens that the combination of these two cancel out to give you the same E. Check it. So that means phi and A cannot be uniquely fixed. They have this huge freedom where chi is any arbitrary function of positions as well as time. So you can take different values at different space-time points. This is anything unlike that we have seen so far. So far the parameters were just constants in space and time. The lambda mu nu was a constant matrix, the A mu's were constants, right? And such symmetries are called local symmetries or gauge symmetries. So this is the demonstration of one of the things that I was mentioning in the introduction. Now to actually go on to demonstrate the Lorentz covariance of the Maxwell's equations, turns out that you have to package this phi and a into a 4 vector like so. This is again velocity of light, and this was the thing that I forgot to mention earlier. Now it's mentioned. So the 4 divergence is given by partial derivatives with respect to t 1 over c and the gradient, and when you raise this index, this picks up a minus sign, this remains the same. Similarly here, when you raise this index up, this minus goes to plus, and that remains the same. And a more natural way to think about it is in terms of 1 forms, but I am going to skip that. Okay. So written in terms of A, you can define a matrix called F mu nu, which is del mu A nu minus del mu A mu, which comes from this definition, and then simply calculate using the definition of A mu and del mu, write it in terms of E's and B's. This is another exercise that you should do. F mu nu takes this particular form. So 0I elements are electric fields. It's antisymmetric, manifestly antisymmetric. So these are opposite to these, and these so Fij is related to Bi epsilon ijk, Bk epsilon ijk, where epsilon ijk is the Levi-Civita symbol in 3 dimensions. Okay. Maybe there is a factor of half somewhere. So once you write it in terms of this, then the 4 equations that we were missing can be written like so. Del mu F mu nu 0. F mu nu up now, so you have to raise these indices. All that it means is that all these will become plus, all these will become minus. Then you should check that these equations, when written in terms of E and B, are exactly these equations. So that means we have written the remaining 4 Maxwell's equations in a covariant form. What it means is that once you make appropriate transformations of F, the form of the equation remains the same. In the presence of sources like electric charges and magnetic currents and so on, so the right hand side will not be 0, okay, but we will not consider that. Okay. So, but these equations are actually Poincare invariant. Okay, so what it means is that this is why I derived the 2 representations I wanted, one in terms of the differential operators. Okay, these 2 are the differential operator representations which act on the coordinate dependence. Now this is a 4 coordinate dependence as opposed to 3 coordinate dependence on this, and this guy, which was a 4 by 4 matrix, acts on this index. So there is a simultaneous transformation of A as if it's a 4 vector through 4 by 4 matrices, and also as a function. And as I said, in terms of 4 by 4 matrices, P is not faithfully represented. So there is no term corresponding to P's, whereas in terms of differential operators there is. This is the P, del mu. Remember that, right? P was there, and the total variation was this. So. Okay, so again it's an exercise for you to check that under this variation this equation remains invariant, the variations of this. But there is another way. We don't do this in terms of, okay, we can also do it in terms of action, maybe it will come later. But before that I want to mention one duality, the very famous duality. If E by C goes to B and B goes to minus E by C, meaning what appears here are interchanged with what appears in this 3 by 3 block in an appropriate way, the equations get interchanged. So this equation will be identically satisfied now, and the equation that was identically satisfied becomes this equation. Okay. Should I repeat that? Fine. Okay. This is a very good question, and whenever you say, should I repeat that, nobody will say yes, because people think that only they don't understand, everybody else understand it. I'm going to use that. Okay. So that's the perfect, okay, I'll skip this. This is in terms of forms. I don't have time to explain that. So this symmetry is an example of a duality. You could describe a given electromagnetic system in free space either in terms of these fields E and B or these fields E and B. This is called electric magnetic duality. Unfortunately, this is not an exact duality, it doesn't survive quantization, but it does survive in a different theory which is a glorified big brother of this, which is called n equals 4 super Young's theory, which requires supersymmetry, and non-abelian gauge symmetry, and so on. Again, I'm only going to mention this because I'm towards the end of my talk. Okay, so what about, so we have seen Poincare invariance for Maxwell's equations and gauge symmetry. What about charges? What about the Lagrangian? Where is the power of it, right? So the power of it comes from saying that, suppose I give you an exercise to a graduate student or somebody, construct for me an action or a Lagrangian which is Poincare invariant as I have specified, and gauge invariant, and leave it as an exercise with no parameters, no additional parameters. You have no choice but to write down this Lagrangian, apart from this overall constant which is not fixed by symmetries. F mu nu, F mu nu. All the indices being contracted, it just reflects that it's Lorentz invariant, but it's actually Poincare invariant as well, and that's built into this construction. Poincare transformations don't act on F. Okay. And then the corresponding action is this, and then there's a generalization of Euler-Lagrange equations, there's a generalization of Hamilton's principle to field theories, and if you use that, gives rise to this equation of motion. And again, I'm not going to explain this. This is towards the last part of my talk, so if you're seeing it for the first time, make a note and try to figure it out if you're interested. You can immediately show that this gives rise to these 4 equations. So you see mu is contracted, mu is summed over, only floating index is nu, so there are 4 equations, and these are the 4 equations that makes it only plausible. Okay, so that ends showing that Maxwell's equations and the Maxwell's theory without sources, in fact it's also true with sources, is covariant under Poincare transformations. But from now on I'm firmly setting all the sources to 0, okay, and show that it has bigger symmetry, which is conformal symmetry. This is apart from gauge symmetry. Gauge symmetry survives with or without sources. Any questions? This is the last part, last 10 minutes. No? Okay. Very good. So this is conformal group. So it turns out that the action that we had written down is not only Poincare invariant, the symmetries is not just Poincare, it's much bigger, it's conformal symmetry. But for that I need to warm up a little. So the way, there are several ways of defining conformal symmetry. Maybe you will see some other definition later on today. Okay, this is the definition I'm going to work with. So these are the coordinate transformations, okay, which leave the Poincare invariant metric, the line element ds2. Now I'm switching over to metric being eta mu nu as opposed to ds2, which was the line element. Those transformations which left the line element, okay. So I need to generalize those coordinate transformations which leave the line element or the metric invariant only up to an allowed overall factor which need not be a constant. This is called conformal factor. So if the coordinate transformations are such that the line element only gets scaled by an overall factor, could depend on space-time coordinates, but not arbitrary space-time dependence, as we will see. Okay, such coordinate transformations, I'm going to call them conformal coordinate transformations. This is my definition. Okay, so then this is something that I did not explain so far. So if you had a metric like that, and if it has to respect some kind of coordinate transformations, then its transformation has to be like this. The new metric has to be given in terms of the old metric in this fashion. This bracketed quantity, I'm sorry, I apologize, I'm not explaining this. This bracketed quantity is called the Lie derivative of this guy along this vector psi. But that's, but there's an explicit expression here. I don't even have to use this. All that I'm interested in is when g is eta, because I can work with Cartesian coordinates all the time, where eta is a constant, and in which case I would have the same variation as earlier. I don't know why I put this here, maybe I did that after this. So remember, this is the variation we had found, right? So I could just use this. So for the line element to pick up a factor means that this need not be 0, unlike here, this is called Killing equation, but this can be something proportional to eta itself. Okay, so that means that the corresponding equation, this psi, the infinitesimal coordinate transformation, has to satisfy, takes this form. This being 0 was the thing which gave rise to differential operators, satisfied the Poincare algebra. But now that equation has been generalized, for some reason I also put a d instead of working with 4. D equals 4 is the case that we have been working with. There are two very special cases when d is 1. This equation means nothing, it's identically satisfied. Okay? So no constraints on psi, but in that case d is 1, meaning there is only one coordinate, which is time. So arbitrary functions of time would have solved that equation because there is no such equation. Left hand side is identical right hand side. D equals 2 is another special case where this equation admits infinitely many solutions again. Okay? They split into two copies of something called bit algebra, the corresponding vector fields satisfy two commuting copies of bit algebra. But our interest is d equals 4. But any d greater than or equal to 3, there are finitely many solutions to this equation. And I've just given you the solution instead of deriving it for you. What I want you to do is to take this and check that they satisfy this for d equals 4 or d equals 3, depending on the dimension. Okay, so this part is Poincare, as we had seen before, provided omega is antisymmetric as this. But there are two more types of terms. One is a real parameter lambda, and there is a 4 vector worth of parameters b mu, 4 vector worth of terms here, where I mu nu of x is a particular combination of the coordinates. I mu nu of x is delta mu nu minus 2 by x square x mu x nu. This happens to be a very interesting object. This by itself is a Lorentz transformation. It's just coordinate dependent. It's some kind of a local Lorentz transformation matrix, 4 by 4 matrix. Okay, so then the divergence term only comes from these two things. This is Poincare space-time translations. This is Lorentz boosts plus rotations. This is called dilatations, and this is called special conformal transformations when you make this coordinate transformation to finite coordinate transformations. These finite coordinate transformations are also known. What was the finite coordinate transformation in the Poincare case? X mu went to lambda mu nu x nu plus a mu. That's finite. All that lambda has to satisfy is lambda transpose eta lambda is eta. Okay. Here the corresponding finite coordinate transformations are these. This was known, this was also known. This is the finite version of dilatation, what I call this dilatation. The transformations which have b mu as parameters are called special conformal transformations. The finite form is this, very highly nonlinear transformation. Unlike these, which are at most linear in coordinates, they are very highly nonlinear transformations. But to show that Maxwell's theory is conformal, the observation that I need is the Jacobian of all these things up to a factor is always a Lorentz rotation, 4 by 4 Lorentz rotation, Lorentz transformation. Okay, so I have given you in small font here. This is of course already a Lorentz rotation. This was a special case of Lorentz rotation, just identity. This is this conformal factor times Lorentz rotation, which is identity. This is the only non-trivial thing that you should do. So start with this and write down the Jacobian matrix. Up to this factor, it can be written in terms of that I matrix that I just told you about. But I told you that I itself is a Lorentz rotation. This is a composition of two Lorentz rotations where the parameters are x and x prime. Note this x prime is a whole thing. Okay. So when you strip this factor off, it's again a Lorentz transformation. Fine. Okay. I think I can safely skip. The point of this is that now you have 15 parameters and the corresponding algebra can be identified with SO 2,4 algebra. It's like SO 6, but it's a pseudo version of that, an indefinite version of that. SO 6 would have had 15 generators, n into n minus 1 by 2, and this also has 15. Why 15? I believe I told you. This is already 10 plus 1 plus 4. Yeah? Okay. Let me skip that. So the main point here is that all the Jacobians are up to conformal factors are Lorentz transformations. Now comes the miracle. Because F is an antisymmetric matrix obtained by del mu a nu minus del nu mu, which is called an exterior derivative of a one form. Okay, it has very nice properties under such coordinate transformations. It just transforms like a tensor does. But if you don't believe what I just said, you can verify this for yourself by starting with how a vector would have transformed, a mu would have transformed under the coordinate transformations that I had given, and then compute till cows come home, and then you can find the infinitesimal version of this, but this is a finite version of that. So what it means is that when F transforms, all that it does is to pull out Jacobian factors. But each Jacobian factor up to a conformal factor, fixed conformal factor, is a Lorentz transformation, right? So when f mu nu is considered, right? So if there were Lorentz transformations, that would have been invariant. If they are not Lorentz transformations, all that you would get is that overall factor we stripped off from each of the Jacobians. That overall factor exactly cancels with the measure factor, how the Jacobian of the coordinate transformation in the action there is a d4x, right? Oops. How this transforms to make the action invariant. So I think again I should apologize, this may be too fast, but I think I've made the essential points. Okay. So this is conformal invariance of Maxwell's equation. So it has 15 parameter worth of global symmetries, because none of the parameters A, omega, lambda or B have any coordinate or time dependence. These are global symmetries in addition to the gauge symmetries, right? Okay, very good. So then the corresponding conserved charges are there. I'll skip this. The last slide is just an advertisement. So the things that I've told you about the conformal symmetry of Maxwell's theory, unfortunately is broken at quantum level and in presence of sources and various things, but there is a big cousin of it, which is a much simpler theory, because more the symmetry, simpler the theory, which is called n equals 4 super Young's theory. Okay, this n equals 4 means that there is some supersymmetry, which I won't explain. Yang-Mills means that instead of working with gauge transformations which commute, you work with gauge transformations which do not commute, successive transformations. You have to keep the order in mind. And then that theory is exactly conformal. Now the conformal symmetry is the algebra is isomorphic to SO2, 4. Okay, it has 15 generators. And then if you wanted to geometrize that symmetry, meaning see it as a symmetry of a geometry. So if somebody gives you SO3, can you think of a geometry which realizes that symmetry? R3 of course, but it's redundant. You take a unit S2, unit sphere, okay, and make an SO3 rotation of this with the center of that hollow sphere left invariant. Okay, then it just maps points to points. Not only that, because there is a ambient R3 which has a metric, which has a line element, that induces what one means by distance between points on the surface of the sphere. That metric will also be left invariant by those transformations, right? So the geometrically SO3 is simpler to, it's not simpler, but it's realized on S2, but in a nonlinear fashion. But yeah. So such a space which realizes this conformal symmetry as a space-time is called anti-de Sitter space, ADS5. What is ADS5? Now I start with R2, 4 instead of R3. I started with R3 and considered a sphere, right, to realize SO3 symmetry. But here I have SO2, 4, so I start with R2, 4. What does it mean? I have 2 time-like coordinates and 4 space-like coordinates. Okay, don't ask me what it means physically. Okay, so start with that and consider some kind of a line element which is like the distance from the origin, and say that distance from the origin is fixed. It's like the generalization of the sphere condition. Distance from all the points which are equidistant from the origin are the points on the sphere. So if I define it like that, and this minus L square, L is a real number, means that the section that I get, the hyperspace that I get, which will be 1 dimension less, that will be 5 dimensional, will have a time direction, and that space is called ADS5. And this ADS5 realizes these symmetries as its isometries. Okay, this is at the core of a very, very fascinating duality between 4-dimensional Maxwell-like theories, Yang-Mills theories, and gravitational theories in ADS5. We have not talked about gravity at all because of lack of time. It's another fascinating theory which is fixed by local symmetries. Okay, but there's a huge, well-developed dictionary which tells you how these two theories could be equivalent, and that's called ADS-CFT correspondence or holography. And at the core of it before you start thinking about it, it's the symmetry considerations most of the time. Okay, so I finished what I wanted to say, so maybe I should simply let yourself to read this. So there are 2 slides of this. I'll stop. Thanks.